Hello everyone, my name is Ismael Arroyo Jr. and I'll be presenting intricate complex numbers. Here's a brief outline. We're going to have an abstract, an introduction to history, and mathematical tools, concept, important theorems, field, an application, and a conclusion. The abstract is basically that you're gonna end up taking a gist of knowledge of complex numbers in a field of mathematics, and we're gonna show some problems that are gonna be followed by that are going to be solved and followed by proofs for validity and arguments, and some more of the arguments, right? So if you ever do 2 plus 2, 3 plus 3, what do you call those numbers in your head? Imaginary numbers? We can't really call them imaginary numbers because imaginary numbers are part of a complex number, right? So you have a plus bi being a complex number, and a being real, bi being imaginary. And it is imaginary because I is imaginary. I, we define it as square root of negative 1. So a plus bi is what we would call a complex number, and a complex number includes basically real numbers. So you usually see the realm of real numbers from negative infinity to positive infinity, but complex numbers is bigger than that, right? It expands it. It expands all your knowledge of numbers, right? And basically it's a new realm. So we're gonna be finding out like what is interesting about complex numbers, and what are some basically that's it. Just investigate what is interesting about it. So around 4 years prior to the catastrophe of Pompeii in 75 AD, Heron of Alexandria was trying to find the volume of frustum. He couldn't find it because he needed to find the height, and to find the height he needed to find the square root of a negative number, and it was just him practicing his math in random pyramids. And so he gave up on this certain pyramid because to him square root of negative numbers was gibberish. It was impossible, so he gave up on this problem. Girolamo Cardano agreed that it was manifestly impossible to find a solution with a square root of a negative number because it was supposed to be imaginary, something that does not exist. So he is important because he is one of the founding fathers of algebra, because he was one of the first publishers of algebraic book. Then Raphael Bombelli comes later on with Le Algebra, his book, where he shows a calculus of operations in terms of I, and uses a problem to show that Girolamo Cardano and his formula to find a certain number, right, or a quadratic, the solutions for a quadratic had a flaw, right, where he showed that using imaginary numbers you can find a real solution, not just a complex solution. And in Girolamo Cardano's formulas, you can only find complex solutions. Now, some math tools that you must know is the commutative law, associative law, additive identity and inverses of real numbers, the commutative property and associative property from multiplication, the multiplicative identity and inverse, and distributive laws and conjugates. If you don't know any of these, you can always pause the video and come back to them. But for conjugates, here's a brief example, which is 4 plus 7i is, the conjugate is 4 minus 7i, right? Pretty simple to understand. Now, important concepts that you must know is derivatives and integrals for one problem that we're going to be showing. So basically, these are the fundamental theorems of calculus. Like, all you're going to need to know is fundamental things, right? For derivatives and integrals. Yeah, so some elementary math and algebra is that basically a complex number is z, which is represented by c is equal to a plus bi, where a and b are elements of real numbers, and I squared is equal to negative 1. Here's how we would add complex numbers in an abstract form, and here's how we multiply numbers in an abstract form. The commutative associative properties of addition work the same way as in real numbers, and the existence of additive identity and the existence of additive inverse work also the same way, just that obviously we have 0 for real numbers and 0 for imaginary, and we also have the inverse for we also have to have the additive inverse for the imaginary part. The commutative and associative properties for multiplication work the same way also. Something interesting is that for the existence of multiplicative identity is that 2 plus 3i times 1 plus 0i, you have to multiply times 0i so you can get the same number, like the identity, according to the identity. And the existence of the multiplicative inverse is the same. You just put it the complex number over 1. The distributive property also applies, and this is how you, like an example of how you would distribute. Here's a little bit of reference for Bambelli's calculus. This is what he found out, that I to the n is equal to I to the n mod of 4, right? So basically found out that there's a cycle going on with the answers for I to the n, right? And so basically he found out this cycle, and that's something that's going to help us out with this interesting false proof, right? The false proof is that it shows that 1 is equal to -1 using this problem, that 1 over -1 is equal to -1 over 1, where they conclude that 1 over I is equal to I, right? And we prove it wrong because of the square root property, where a and b is equal to square root of a times square root of b. So if we apply the square root property, we have square root of -1 times square root of -1 at the bottom over here. So we multiply both numbers and we end up with 1. So the square root of 1 over this under 1 is still 1 over 1, which is 1. So on the left side we end up with 1, not -1. So some trigonometry and calculus that you must know is that e to the x, cosine of x, and sine of x, they're Taylor series. How they look like, this is how they look like, and their summations. So we're gonna try to find the relationship between the Taylor series of these three functions, and we're gonna assume x equals to it, and this is how we would simplify it, right? And how it would look with it as the power, and this is having even powers and odd powers separated, and we can factor out an I. When we do that, we can show that cosine of t is the top summation, and that sine of t is the bottom summation with a factored I, right? And this gives us the polar form of e to the it, which is cosine of t plus I sine t. And when we apply pi to t, to that angle, we end up with Euler's formula. This is important because it shows the 5 numbers that are most important in mathematics, right? Which is 0 and 1, which are identities, and e and pi, which are infinite numbers, and I, which is a complex number, right? Now, Euler's formula was voted to be the most beautiful formula in 1988 by a poll where in a meeting of mathematicians in 1988, right? And that's why it's an important formula to know. Now we can show that e to the I pi over 2 is equal to I, and here is the solution, right? And that I to the I is real, and here we use power 2 powers is you multiply the powers. We show that I to the I is basically I squared, and we end up with a real solution because -1 is real. Then here we show how we convert Cartesian to polar. Here is basically the structure and how we would convert them. Here's a problem for it. 1 plus square root of 3i. We use a equal to 1 and b equal to square root of 3. We find r to be 2 because it's square root of 4, and theta to be pi over 3. When we put the theta into the polar form and the r, we end up with this solution, and the exponential form will basically just get the theta or the angle and plug it into t, right? Here's another way to finding Euler's formula, or we're using calculus. You have to get the derivative of t equals cosine of I sine t. You use Bambelli's calculus next, and then find the integral in terms of x. Then afterwards, you apply the you find the value of c. You end up with that c is equal to 0, and then you make everything have a base of e to cancel out ln, and you end up with Euler's formula. Then we get the well-ordering principle of n. It's a definition, and we need to know this definition because it's important for lexicographic ordering. So for partial order, you have flexi property, transfer property, and antisymmetric property. Those are the important things to know. And for total order, you have this additional property, right? Here's lexicographic order and its definition. You can always pause the video if you need to find out something or see something that you don't understand. For partial order in complex numbers, we have x1, x2, and x3 being complex points, right, in the complex plane. And we show that in A we have the reflexive property, and that we also have the anti-symmetric property because 3, 3i cannot be flipped. It cannot be 3i, 3 because that's not in the plane. Then in B, C, and D, we have the translator property because x1 is less than x2 and x2 is less than x3, and so x1 is also less than x3. And that's what we see right here. Then we have total order. Here's the explanation for it, and we do find that complex number has total order. We have property in R where A is less than or equal to B, and if we multiply both sides by C, we still have them being less than or equal to each other. So we try to find if this property applies in C, and we find out that no, there's a contradiction where Z is less than or equal to W, and it gets contradicted when we have ZU is less than or equal to WU. Then we find out that Heron of Alexandria, we try to solve a problem for it. We're gonna show the application. This is how we find the height, and that's a the height for a frustum, right? And our conclusion is that Heron of Alexandria was right. You can find a frustum of a pyramid with a square root of a negative number, but they are actually you can actually find them in real life. You can actually make them. So Heron of Alexandria, when he thought that they were unreal, they are actually real, and that complex numbers have a lot of math involved in them, like way more than we thought. That concludes our presentation.